Ever wondered what happens when a star collapses under its own gravity? You get a black hole, a celestial object of such immense gravity that nothing, not even light, can escape its pull. Now, let's dive into the enigma of black holes. Picture a massive star, many times larger than our sun. When it exhausts its nuclear fuel, it can't support its own weight and it collapses under its own gravity. This implosion creates a black hole, a point in space where gravity is so strong that it warps the fabric of space and time itself. Imagine a sinkhole in the fabric of space-time. Anything that comes too close, whether it's a stray asteroid or a beam of light, gets sucked in and can't get out. That's the event horizon, the point of no return. Once you cross this invisible boundary, you're inexorably drawn towards the black hole's center. Black holes come in different sizes and types. Stellar black holes, the most common type, are birthed from massive stars. They are typically about 10 to 20 times the mass of our sun. On the other end of the spectrum, we have supermassive black holes which are millions or even billions of times the mass of our sun. These cosmic behemoths lurk at the centers of galaxies, including our own Milky Way. Black holes are fascinating not just for their sheer power, but for the mysteries they harbor. They challenge our understanding of the universe and the laws of physics. They are celestial riddles waiting to be solved. Black holes are more than just cosmic vacuum cleaners. They are laboratories of extreme gravity, offering us tantalizing glimpses into the nature of the universe. They are cosmic time machines, potentially offering a gateway to the past or the future. But at the heart of every black hole lies an even deeper mystery, the singularity. Imagine a point in space where density becomes infinite, and our understanding of space and time breaks down. That's a singularity. Sounds like science fiction, doesn't it? But this is the reality we're dealing with when we delve into the mysterious world of black holes. So let's start by defining a singularity. Imagine trying to squeeze all the water in the world into a thimble. It's impossible, right? But in a black hole, this is precisely what happens. All the mass of a collapsed star is compressed into a single point of infinite density. That's a singularity. It's like the ultimate cosmic crush, where matter is compacted to such an extent that our regular laws of physics just stop making sense. Now, not all singularities are created equal. There are different types, each with its own unique quirks. Let's take a look at two main types: point singularities and ring singularities. Point singularities are the most straightforward. They're just what they sound like. A point with zero size yet holding all the mass of a black hole. It's like the universe's ultimate magic trick, making matter disappear into nothingness. On the other hand, ring singularities are a bit more complex. They occur in rotating black holes, also known as Kerr black holes, and are shaped like a ring. Picture a hula hoop spinning so fast that it warps the fabric of space and time. That's a ring singularity. They're fascinating because they theoretically create wormholes, shortcuts through space-time. But let's not get lost in the wormhole just yet. So we have these extreme points in space where density becomes infinite and our understanding of space and time breaks down. It's a lot to take in, isn't it? But remember, we're only just scratching the surface of the enigma that is a singularity. But what does this mean for our understanding of the universe? The singularity is where our current understanding of physics, particularly general relativity, falters. Let's unpack this a bit. General relativity, the brainchild of Albert Einstein, has been our best tool for understanding the universe's large-scale structure and behavior. It's a theory that describes gravity not just as a force, but as a curvature in the fabric of space-time caused by mass and energy. This theory has been incredibly successful, predicting phenomena like the bending of light around massive objects or the time dilation in strong gravitational fields. However, when it comes to singularities, general relativity hits a roadblock. It predicts that within a black hole, matter is crushed to an infinitesimal point of infinite density, warping space-time to an extreme degree. This idea of infinite density, though, doesn't sit well with our understanding of the physical world. It's here that general relativity, as we know it, breaks down. This is what we call the singularity problem. It's a gap in our knowledge, a chink in the armor of our current physics. but it's also an invitation for new theories, new ways of looking at the universe. Enter the world of quantum gravity. Quantum gravity is the sought-after theory that would reconcile the large-scale predictions of general relativity with the small-scale world of quantum mechanics, the theory that governs the behavior of the tiniest particles in the universe. Two prominent theories are loop quantum gravity and string theory. Loop quantum gravity suggests that space-time is not a smooth continuum, but composed of tiny, discrete loops. On the other hand, string theory posits that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. Both theories offer intriguing insights into the nature of singularities. They hint at a universe where the singularity, instead of a place of infinite density, could be something entirely different. Yet these theories are still in their infancy, unproven and subject to intense debate. But it's not just theory that's grappling with the singularity. How can we observe something that by definition is unobservable? Indirectly, of course. The very nature of singularities makes direct observation impossible. But that doesn't stop us from unearthing their secrets. How do we do it? By observing the effects they have on their surroundings. Take black holes, for instance. We can't see the singularity at the heart of a black hole, but we can see the effects of its intense gravitational pull. Gas, dust, and even light get sucked in, creating a dark void in space. Surrounding this void is a bright disk of hot, swirling matter called an accretion disk. The extreme conditions here produce X-rays, which we can detect from Earth. By studying these X-rays, we can infer the presence of a singularity. But that's not all. The Event Horizon Telescope, a global network of radio telescopes, gives us even more observational prowess. In 2019, it captured the first-ever image of a black hole's event horizon. While we can't see the singularity itself, this image provides valuable clues about what's happening inside the black hole. Looking ahead, advancements in technology and observational techniques promise to shed more light on these enigmatic entities. Gravitational wave astronomy, for instance, could provide us with fresh insights into the nature of singularities. However, it's important to remember that our understanding of singularities isn't set in stone. Alternative explanations have been proposed, challenging the conventional view of a singularity. Some theorists suggest that what we think of as a singularity could actually be an exotic object, something entirely different and perhaps even more bizarre than a point of infinite density. These alternative interpretations add another layer of complexity to our quest to understand singularities, but they also highlight the beauty of scientific inquiry. The more we learn, the more questions we uncover, driving us to push the boundaries of our knowledge. Yet the singularity doesn't just challenge science, it challenges our very understanding of existence. The singularity not only challenges physics but also presents profound philosophical questions. What does it mean for our understanding of space, time, and existence? The singularity, a place of infinite density, where our familiar laws of physics cease to apply, forces us to reevaluate our concepts of reality. It's a point in space and time where everything we thought we knew about the universe breaks down, a place where the rules are rewritten. The singularity has also found a place in the realm of science fiction and popular culture, often depicted as gateways to other universes or times. The idea of a point of infinite density where time and space are distorted beyond recognition has captured the imagination of writers and filmmakers, giving birth to a myriad of stories and narratives. From the mind-bending journeys through wormholes in Interstellar to the destructive force of black holes in Star Trek, the singularity continues to inspire awe and wonder. Yet despite its popularity in fiction, the singularity remains a largely unexplored territory in actual science. There are still many open questions that need to be addressed. What exactly happens at the singularity? Can we ever develop a theory that accurately describes it? Is it possible to observe or measure anything beyond the event horizon? These questions present exciting avenues for future research and exploration. Scientists are already working on potential solutions, from quantum gravity theories to the idea of exotic objects within the event horizon. New technologies like the Event Horizon Telescope are being developed to probe the vicinity of the singularity and provide us with more concrete evidence of its existence. The singularity, a point where our universe as we know it breaks down, continues to be a fascinating enigma, pulling us towards a deeper understanding of our cosmos. As we continue our journey into the unknown, the singularity stands as a testament to the infinite potential of discovery, a reminder that there is always more to learn, always more to explore. Who knows what secrets the singularity might reveal in the years to come?